Okay, now in this slide, what I have is just a list of common graphs. Now, I don't write common graphs of functions because almost all of these are functions except for one. And then I'm going to ask you if you can identify which one it is. But basically, there's a couple functions here that graphs that you should have seen before, and that it's good to just have an idea of how they look like so you can graph them really quickly. So have y equals x. It's a line going through the origin. And again, the origin is the point 0, 0. Y equals x squared, y equals x cubed, y equals absolute value of x. We'll talk more about this function a little bit later because it confuses students a little bit. Y equals 1 over x. Right? And then we'll talk again more about the domain and range of this function. Y equals square root of x. Right? We graphed this one already. And if you can see, the graph here matches the graph that we drew. Right? It's basically the same graph. Y equals b to the x. This is an exponential function. We'll talk more about them later, as well as logarithmic functions. And then this is the one that is not a function. That's why I put it in a red box. Now, let me ask you something. Can you identify why this is not a function? So what property do you see about this function, about this graph here, that is different to all of the other graphs? And then if you don't know what it is, it's fine, but let me show you something here. And actually, I think it's better if I just do it in a different setting. All right, so this is the equation in general of a circle of radius r. Actually, in this case, 1, 2, 3, the radius is 3. All right, so this is wrong. This is actually 9. Right, x squared plus y squared equals 9. But in general, if you want to graph, and now this thing here, you'll see that it's not a function once I graph it, right? So for now, I'm just going to say the relation. Suppose we want to graph this relation, x squared plus y squared equals 1. Well, this is basically, and we'll go over this later, but this is basically just a circle of radius 1. The radius is the distance from the origin to the height, or the furthest distance from the origin to any point on the graph. And that's usually how a circle is defined. So this is just this circle here. Now, how do I know that this graph, or this relation, x squared plus y squared equals 1, is not a function? Well, you can easily see that there are some input values that are mapped to more than one output. For example, suppose that we want to see where 1/2 is mapped to under this relation. So how do we verify something like this? We know that we're looking for order pairs that satisfy, oops, I don't know why I did that. We're looking for order pairs that satisfy this relation here, x squared plus y squared equals 1. So how do you determine what's the what corresponding y value corresponds to 1/2, or y values if there's more than one, in which case it wouldn't be a function? Well, can you just plug in 1/2 into this equation here and solve for y? So if I do this, I get 1/2 squared plus y squared equals 1. Now 1/2 squared is 1/4. Just multiply 1/2 times 1/2. Just y squared equals 1. We want to solve for y, so subtract 1/4 from both sides. 1 minus 1/4 is 3/4. And then now what we're going to do here is, okay, we're looking for a number, y, such that when we square it, we get 3/4. Well, there's actually two solutions for this equation. So if we're looking at this equation here, the two solutions are, okay, so we can use square root of 3 over 2, right? This works. If you square this, you get 3/4. But if you square negative root 3 over 2, you also get 3/4. And that's what we see going on here. Right? If you look at this graph, there's a y value here corresponding to 3/4. So this is the point 1/2 comma 3/4. Wait, not 3/4. Root 3 over 2. And then this point here right? On the graph corresponding also to x equals 1/2 is the point 1/2 negative root 3 over 2. Right? So in this case, the input 1/2 is mapped to two outputs. So x, oops, it looks like a y. X equals 1/2 is mapped, by whatever this relation is called. I haven't given it a name, but this is just a relation. So x equals 1/2 is mapped to y equals root 3 over 2 and y equals negative root 3 over 2. Since it's not mapped to a unique element, but it's mapped to two different things, this relation is not a function. And then if you look at the original graph that I have here in this picture, how can you determine, if given a graph of a function, whether an input is mapped to more than one output? Well, we do that using something called the vertical line test. And it's very easy. Draw a vertical line anywhere in your graph. If that line crosses the graph more than once, then your relation or your graph does not represent a function. It's just a relation, but not a function. So you can see here very clearly, and if I draw this vertical line in a lot of places, right, in so many places, it's always going to cross more than once. Right? So this is not a function. However, in all of the other graphs that I have here, it doesn't matter where I draw this vertical line. It's always going to cross the graph at most once. And you can test that doesn't matter where you plot, where you do this vertical lines, it's always going to cross the graph once. Doesn't matter where you do it. So all of these graphs here represent functions. And that's how the vertical line test works. So let's go to another slide, and let's call it the vertical line test. So it's very simple. So let's call it let's not call it a definition, let's just give it this name. So given the graph of some relation, let's give it a name in this case, some relation G between the sets. Let's call them S and T. And now in these graphs here, the input set is always the real numbers, not necessarily the domain, but the input set is the real numbers, and the output set is also the real numbers. Again, not necessarily everything. And in fact, you can see in this example here, I didn't ask you to plot to determine what the range is, but if you look at this example here, just the way I graphed it, the range is just all positive numbers, including 0, just a set of non-negative numbers. It's not possible for us to draw this graph with a negative value. So to draw this graph below the x-axis. So this is an example of a function that maps the real numbers into the real numbers, but whose domain is the set 0 to infinity, and we'll talk more about that notation, and the range is the set 0 to infinity. So the vertical line test. Given the graph of some relation G between the sets S and T, you can determine, or to determine, if the graph of G represents a function, or if G represents a function, what do you do? If a vertical line crosses the graph more than once, then G is not a function, it's just a relation. And then conversely, or on the other hand, if any vertical line, so A or any vertical line crosses the graph of G at most once, right? So it could cross it once, it could cross it 0 times, then G is a function. So it's as simple as that. Okay, so now let's apply the vertical line test to two examples. Okay. So example 8, determine if the following are graphs of functions. Right, so all I drew is I drew the xy plane. I didn't draw any dashes because they're not going to be necessary for this. Right, we don't need that much precision. I just drew how the graphs look like if we graph them. Okay, so these are relations for sure, right? And again, for unless stated otherwise, the domain set, or the, sorry, not the domain set, the input set is a set of real numbers, and the output set is a set of real numbers. That's usually what the xy plane represents. So if we want to determine if the graph of this first graph is a function, just try the vertical line test. If you can draw a vertical line that crosses this graph more than once, then it's not a function. Well, you can easily do that. In fact, this line here crosses the graph 3 times. So this graph, or this is not the graph of a function. Right, now let's go to the second picture. Now you can check and you can convince yourself that it doesn't matter where you draw a vertical line. This vertical line is never going to cross this graph more than once. Never. Doesn't matter where you draw it. So in this case, this is the graph of a function. So very easy. It's as simple as that. So it's a very easy tool, again, to determine, given a graph, whether it's a graph of a function or not. Okay, now let's move to another example. So given the function f, with input set the reals and output set being the reals, that is given by f of x equals x squared plus 2, find the following. We want to find f of 1, f of negative 2, and f of x plus h. Now, I'm going over this example because it's good to remember how to evaluate functions, and because it's included in the section 1 homework. So let's go ahead. Now, anytime you see something like this, where it says f of 1, and you're given the function, right? In this case, we're given the function x squared plus 2. All this means is anytime you see an x, replace it with a 1. That's what f of 1 means. And that's how you want to think of it. Right? So f of 1 is going to be equal to, okay, anywhere I see an x, replace it with a 1. So I have 1 squared plus 2. 1 squared is 1, plus 2 is equal to 3. Same thing with 2. It's always the same thing. Every time you see f of something, that means wherever you see an x, replace it by negative 2 in this case. Right? So if we're doing f of negative 2, what is this equal to? Well, I see an x, so I have negative 2 squared. And this here is important. This is a place where a lot of students make a mistake. If your number has a negative, and you're squaring that negative or taking any power of that negative, make sure to use parentheses when you plug it in. Right? Always. Right? Because you don't want to square, or basically the idea is, let me do it here, negative 2 squared is not equal to negative 2 squared. What is this one equal to? This is negative 2 times negative 2. What is this one equal to? This is negative 2 times 2. This one here is equal to positive 4. This one is equal to negative 4. Right? So anytime you're squaring or taking the square root or doing something like that for a number, make sure that whatever you're plugging in and that you're replacing x with, that you use parentheses to include everything. Okay? So in this case, when I plug in when I find f of negative 2, and I'm replacing x with negative 2, I make sure to square everything, the whole number. And the whole number in this case is negative 2. Okay? So I have negative 2 squared plus 2. Well, negative 2 squared, I remember that squaring means, and we saw it here, squaring just means multiply a number by itself. So negative 2 times negative 2, the negatives cancel. 2 times 2 is 4. So we get 4, and then plus 2, which equals 6. And then for the last one, this one's a little bit trickier, but again, you just want to follow the same process. Anytime you see f of something, all that means is replace x with whatever is inside the parentheses. So in this case, if I want to find f of x plus h, this is telling me, look at the function. Anywhere you see the variable x, replace it with the quantity x plus h. So let's look at the function. I have x squared plus 2. Okay, I see an x. So I replace that x with x plus h, and I'm squaring that. And this is similar to what we were talking about in the previous part, right? You want to make sure that you square the whole quantity. Just as you squared negative 2, not just the 2, right? You want to square all of x plus h. And then plus 2. Now you could leave it here. If they ask you to simplify, you could multiply this out. So again, by definition, whenever you see something squared, that just means multiply it by itself. Now, if you remember how to FOIL, right, or how to multiply things like this, basically you do outside times inside. So that's x times x, that's x squared, plus outside times outside, that's x times h, that's xh, plus, let me do a different color now. Let's do green. Plus inside times inside, right? So h times x. And multiplication is commutative. Right? If you remember what commutative means, it means that it doesn't matter in which order you write the terms. Right? Same with addition. Addition and multiplication doesn't matter in which way you write the terms, it's the same thing. So when I say h times x, it's the same as x times h. And finally, inside times outside, that's h times h, that's h squared. And we still have the plus 2. Now, if you want, you can combine like terms. So we have x squared. Actually, let me use a different color. We have x squared. Here we have xh plus xh. There's 2 of them. So you can write that as 2 times x times h plus h squared plus 2. Now, usually you'll see expressions like this where you want to evaluate something of the form x plus h, where x is a variable and h is also a variable. You'll see this a lot in Calculus 1. I'll talk more about this later. I'll give you examples like this. But for now, what I want you to understand is if they ever ask you to evaluate a function, all you do is look at whatever's inside the parentheses, look at your function. Wherever you see an x or whatever the variable is, replace that by whatever's inside the parentheses, which in this case was x plus h. Okay, there's one more topic to cover in this section. It's kind of similar to determining whether a function is, or whether a relation is a function, right? In the sense of how you do it. But basically, we're looking for one-to-one functions. Okay, so what does it mean for a function to be one-to-one? Now let's see what definition are we looking at. Okay, so I think this is definition 4. Okay, so what does it mean for a function to be one-to-one? A function is one-to-one if every element, so actually let me say a function f, just to keep the notation that we've been using. A function f mapping a set S into a set T is one-to-one if every element of the range of f, right, so the elements of T that have something mapped to it by f, has exactly one element mapped to it. Okay, that's what it means for a function to be one-to-one. Look at a function mapping an input set S to an output set T. It's one-to-one if every element of the range of this function has exactly one element mapped to it, not more than one, right? Just exactly one. So let's do an example. So this is pretty straightforward to check. So example, I think it's example 10. So I'm going to give you, again, this definition. Let's see. Let's say we have the elements 1, 2, 3, 4, A, B, A, B, C, D. And let's say that I have, okay, say that 1 is mapped to A, 2 is mapped to A, 3 is mapped to B, and then 4 is mapped to D. Now, looking at this relation, you can verify that it is a function, right? 1 is mapped to A. Actually, let me just write this. F of 1 equals A. F of 2 equals A. F of 3 equals B. F of 4 equals D. So definitely, every element of the input set is mapped to a unique element of the output set. Right? So it is a function. If we were to graph this somehow, this would pass the vertical line test. Now, what's the range of this function? So the range of this function is every element that has something mapped to it. Right? So A has something mapped to it, B has something mapped to it, not C, and D has something mapped to it. So how do we determine if this function is one-to-one? Look at the range, right, which we found. If any element of the range has more than one thing mapped to it, it is not one-to-one. Well, here we can see that the element A has more than one thing mapped to it. Why? Because 1 is mapped to A, and 2 is also mapped to A. So, since A has more than one thing, more than one element mapped to it, this function is not, it is a function, right? It passes the vertical line test, and you can see that every element is mapped to a unique element of T, every element of S. However, it is not one-to-one. Right, so it's very easy to check if you're given something like this. It's also very easy to check if you're given a graph. Example 11. Let me write, is the function f with input set being the real numbers, output set being the real numbers, given by f of x equals x squared, 1 to 1. Well, in order to do something like this, the first thing you would want to do is graph this. You can look at the table that I gave you of common graphs, but basically, if you graph this, and in terms of graphing, let me give you an advice. Always start like this. Always draw the x-axis, the y-axis, and always label them. Always label the x-axis with an x, the y-axis with a y. But basically, if you were to graph something like this, the graph, so you graph the ordered pairs, connect the dots, and basically this graph looks something like 1, 2, 3, 4, so something like this. Looks something like that. Now, given this graph, just how it looks, how can we determine if it's one-to-one? Well, we want to check if there's any element of the range with more than one thing mapped to it, then it's not one-to-one. Well, let's look at these 2 points here. This is the point 2, 4, and negative 2, 4. So notice here that both negative 2 and 2 are mapped to 4. Hence, we have an element of the range that has more than one element mapped to it. So this function is not one-to-one. How do you see this graphically? Well, you use something called the horizontal line test. So it's very similar to the vertical line test. So horizontal line test. What does this say? If you are given the graph of a function and again, anytime we use the xy plane, we're thinking of a function mapping the real numbers to the real numbers. So a function f mapping the real into the reals, right? Or some subsets of it. If you, or let me write like this. If you can draw a horizontal line that crosses the graph more than once, then the function is not one-to-one. And then conversely, if every horizontal line crosses the graph at most one time, so one time or none, then f is one-to-one. So for example here, you can clearly see that this function is not one-to-one because basically anywhere you draw a horizontal line is going to cross the graph more than once. So in summary, the vertical line test is to determine if a relation is a function. The horizontal line test is to determine whether a function is one-to-one.